Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization, Oil Refining Optimization Advanced Analytics Solutions. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. The central process of tactical optimization of production and energy management is related to the integration of the two systems, through integrated mathematical modeling. Hypothalamus AI considers the production process as a union of two processes: product transformation, conversion of barley into commercial products, through processing units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, or energy producers, in the service units. To optimize energy efficiency, the first step is to optimize the integrated supply chain, since this is the part of the production process that consumes more economic resources. This lecture focuses on the mathematical modeling of service plants. High oil ref includes a generic model that can serve to plan, at the aggregate level, the crude and/or biomass refining processes. The level of aggregation is fundamentally related to the nonlinearities associated with this type of process, but not with the level of detail with which it is possible to represent the production processes, which can be spatially detailed in all units used in the production of refined products. The objective of optimization is to determine the production plan that meets the demand for refined products, according to an offer of available crude types during the planning period. Industrial services optimization is the complementary model to the production model, aimed at optimizing energy management in industrial plants that include large-scale industrial service plants, such as refineries, petrochemicals, oil and gas production, and oil and gas transport. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. These services often include self-generation, cogeneration and the exchange of energy with the interconnected electricity system. The objective of the model is to minimize the consumption, or cost, of the energy required by the industrial processes, supported by the industrial services plants. The industrial services system is coupled with the production process model to holistically optimize the transformation of crude oil into refined products. Demand fluctuations are typical of utility or thermoelectric plants in petroleum refineries. Among the major causes are changes in the oil feed properties, multiple operational campaigns, maintenance of process units, interruption of electric energy supply, and cost variations of fuels and electric energy. On the other hand, utility systems are essential for the operational feasibility of refineries. They and must continually adapt their production levels to satisfy such dynamic demand patterns. Therefore, the designs of utility plants tend to present a high level of flexibility, thus allowing multiple operational configurations that satisfy the same demand targets, sometimes with significantly different operating costs. It is important to note that the operational management of services plant, it is a complex process that benefits from the use of optimization technology. The main entities of the system are: process plant, place in which various industrial operations are developed, including unit operations, to transform, adapt, or treat a particular raw material, to obtain products of greater added value. Service plant, place where various industrial operations, related to the auxiliary services demanded by process plants are developed. Auxiliary service, essential services for the operation of any production system, they allow to guarantee the quality and the continuity of the process, and service unit, facilities that make up the service plant, its function transform the different services to adapt them to the requirements of demand for auxiliary services of the process plant. The main objective is to optimize the management of service plants by considering the fluctuation of demand over time. The classification of the services demanded by different processes is described in the table. They are water, electrical energy, steam, and fuel. The processes that govern energy exchange and fluid dynamics are nonlinear processes. The optimal point of operation of the units of the service system varies depending on the flow, the temperature, and the pressure handled by the unit. Efficiency is a nonlinear indicator of great importance, with which the amount produced can be related compared to the amount of raw material used. For the management of this indicator, it is necessary to manage an adequate data acquisition system, which ensures the correct measurement of the parameters that facilitate its use. In service plants, we find different types of units that interact and interconnect with other units to transform one service into another service. Different types of service units are used to describe the process, although the diversity of units is clear, and the functionality of each of them. Within the modeling, they will be considered as a single entity, characterized by the value of the parameters that define it. These parameters refer to input, product, and driver. The table presents the main units that make up the service plant, and their basic functions. Units such as pumps, boilers, accumulation tanks and valves, condensers, manifolds, steam turbines are specified. There are other fundamental elements for the proper functioning of the service plant, such as the measuring units to control the operating conditions of the units, such as pressure gauges, thermometers, water level indicators, flow meters for steam, alarm and control devices, among others. These elements are not handled as entities within the mathematical model that represents the service plant, but they are of great importance, since they make up the data acquisition system, fundamental to the state estimation modeling process. The image presents the variables that give continuity in the flow in the U boiler. The flow variable is CVC UO UD, where UO, origin unit UD, destination of, and A, service. The process involves 5 units, 2 origins, 2 destinations, and the unit that connects them. The process includes 4 services, 2 inputs, and 2 outputs. The image presents the connection of service units and flow variables. The interaction of the auxiliary services plant with the industrial process plant is carried out through the demand made by each process unit. This demand can be exogenous, when the industrial service plant optimization model is connected in series with the results of the industrial process plant models. This type of connection is called coordinated. If optimization is performed integrally in a single model, the demand will be one of the decision variables of the model. This type of connection is called integrated. Integrated models, if they can be solved, produce greater benefit than coordinated ones. If optimization is performed integrally in a single model, the demand will be one of the decision variables of the model. This type of connection is called integrated. Integrated models, if they can be solved, produce greater benefit than coordinated ones. In a services plant, services units fulfill specific functions. In the figure, we can see producing units, collecting or distributing units, and consuming units. External services that are not produced in the plant, supplied in some cases by the process plant, must be considered. For example, the refinery supplies fuel oil, gas, and steam to the service plant, or by service providers, which can be modeled as an external unit. In a services plant, services units fulfill specific functions. In the figure, we can see producing units, collecting or distributing units, and consuming units. External services that are not produced in the plant, supplied in some cases by the process plant, must be considered. For example, the refinery supplies fuel oil, gas, and steam to the service plant, or by service providers, which can be modeled as an external unit. The simultaneous optimization of both industrial production and energy conversion is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. HI may integrate complex industrial process models to redesign the power supply system, according to the new power technologies. This type of model includes the simulation of polluting processes to determine the optimal mixture of fuels, in accordance with environmental regulations. Considering that the energy market allows the integration of multiple factories of different types, all composed of process plants and service plants, it is possible to integrate all the optimization process, physically integrating the service plants, and virtually the transactions in the markets. This is the real problem of a global and/or multi-business company. Case: Industrial Services Optimization. This is an academic example of the high ISO model, developed by High, for a company in the oil sector. The diagram presents the service plant considered for the academic example. The model was applied to an oil production field, and its service plant. The diagram shows the connectivity of the system that provides electricity and steam, and consumes fuels in its production. In addition, it connects to the national electricity grid to buy or sell electricity. To simulate the electricity demand, in the national electricity grid model, each consumption node has its own demand, and its own load curve, or load duration curve. In general, it is assumed that a typical day is simulated, for each node and for each period of the simulation horizon. To consider daily seasonal variations, it should be noted that there are no limits on the number of blocks into which the period can be divided, therefore, multiple typical days of consumption can be dispatched, example, holiday or Sunday, Saturday, and business day. Load blocks can be associated with a sequence of hours, and can be associated with power plants, mainly water edges, for which a daily operation cycle is planned. Since the load and prices of electricity vary during the day, in many cases it is desirable, or necessary, to synchronize the operation of the services plant with the electricity market at the regional, or national, level. This is since energy flows can change during the day. The graphs show the prices of electricity and steam. In this case, 5 load blocks are considered for each period of the planning horizon. The price of steam is considered constant per period, while the price of electricity is discriminated by 5 blocks. The highest price will be the block 1, with the highest load, and the lowest price will be block 5, with the lowest load. The price of gas is uniform by period, but varies significantly throughout the different periods. The lower the availability, the higher the price. One of the results is the optimal dispatch of generation units, which will vary by period and by block. Since electricity is dispatched by block, the same will be true for natural gas. Another case in which mathematical models are effective, it is in the expansion of service plants. In this case, the installation of 1 or 2 additional thermal plants is being studied, and its connection with the national interconnected system. The graph presents the results of the dispatch of the existing thermal plants. The analysis of the projects was carried out under the following scenario. Fuel availability is restricted, and 50% increase in electricity demand projections. For the cost of dispatch, the results were $39.69 million with projects, and $40.105 million without projects. The difference was 1.02%. The graph shows the dispatch of the 4 finished thermal plants. As you can see, the project A is not used. The analysis of the projects was carried out under the following scenario. Fuel availability is restricted, and 50% increase in electricity demand projections. For the cost of dispatch, the results were $39.69 million with projects, and $40.105 million without projects. The difference was 1.02%. The graph shows the dispatch of the 4 finished thermal plants. As you can see, the project A is not used. Case: Integrated optimization in Petrobras. This case is based on the paper Operational optimization of the utility system of an oil refinery. Petrobras Recap Refinery develops a mathematical programming model, applied to the operational planning of the utility plant, as well as its interconnections with the process units. The problem is formulated as a mixed integer linear programming, MILP, model where the mass and energy balances, the operational status of each unit, and the demand satisfaction, are defined in multiple time periods. The model determines the operational configuration of the plant, by minimizing utility costs, and identifies steam losses as well as inefficient units by comparing the optimal solutions with the current operation. The MILP can accurately represent the topology, and optimize the operation of the real-world system, under different utility demands and abnormal situations in single and multi-period scenarios. Continuous and binary variables are defined for the proposed model. For instance, continuous variables represent the flow rates between the units, whereas binary variables denote the operating state of the unit, on or off. These variables are defined for every period t of the horizon considered. It is assumed that the units and external sources, for example electricity concessionary, can complement internal generation, and therefore supply the sets of variable demands in each period. Description of the utility system. The figure presents the simplified flowchart of the recap central utility system, in which each unit connected to utility header UT is represented by a rectangle that contains its identification. This configuration considers only the systems that are subject to optimization. The initials used to identify the entities of the system are J pumps and ejectors, GV or L furnaces and boilers, M heat exchangers, O or P vessels, TF valves, and V blowers and compressors. The utilities that are considered in the optimization problem are superheated steam, V30S, saturated steam, V30, and its condensate, CV30, bar steam, V5, and its condensate, CV5, and bar steam, V1, and its condensate, CV1. There are also two other headers for condensate, that are CVV and CM, which originate from the vacuum system of the process condensation turbines. The images present the indexes and are set using in the model. Therefore, units with fixed operation do not need to be modeled and their operating variables, they are simply included as parameters that are calculated from material and energy balances. For a given header of utility UT, their aggregated values are given as a summation in the term denoted UTCF. An example of the simplifications introduced to represent the headers is shown in the figure. For the case of the V30S network, each unit is represented by a rectangle that contains its identification, and it is associated to the branch that symbolizes the process area to which it belongs. The minus sign under each rectangle indicates V30S consumption, whereas +sing denotes its production. The figure 2b shows the modeled system. The variables used are presented in the image on the right side. They are identified by their first letter. E continuous energy flow rate, Q continuous heat received from external sources, it is only positive for the boilers, 0 for all other units, V continuous volumetric flow rate, Y binary, equal to -1 if unit operates in period T, 0, otherwise. The images present the parameters used by the model. A unit may produce and consume one or multiple utilities. If a unit produces utility UT, it is sent to its corresponding header. Similarly, if utility UT is consumed in a certain unit, it is sent from its corresponding header. The figure generalizes this idea for every header of utility UT, denoted by CLUT. In this figure, the utility stream UT that is generated in unit EQ is sent to header CL UT at time t with flow rate VEQ UT CLUT T. This header receives all the streams of utilities that are produced in the same time period from all EQ that are mixed at the temperature and pressure conditions of the header. Similarly, header CLUT sends utility UT at time period T to consumption units. A decision variable YEQT is associated with flow rate variable VEQ UT ET. The image presents the main service units included in the model: boiler, vessel, pump with electrical drivers, and pump with turbine drivers. The cases presented are applied to single period operation. In other words, there is one set of utility demands to be satisfied, which is obtained from the data acquisition system, and thereon the configuration of the plant is optimized. Different single period scenarios are considered. Firstly, the model was validated to verify consistency of the formulation, basically by eliminating the degrees of freedom and providing reference values for the economic objective function as well as for the operating conditions of the optimization model. For this reason, 3 base cases were developed: base 1, base 2 and base 3, that correspond to 3 different operational conditions of the plant. Cases base 1 and base 2 correspond to operational conditions of the plant in typical days, without abnormalities. The objective in this study is to validate the model, and to evaluate the effect of the manual planning in the operation, in particular its economic impact. Case Base 3 considers an atypical situation given by the shutdown of U-570, which generates a large portion of EE as well as V30 and V30S. The table presents the comparison of the base cases with the solution of the mathematical model. 1 means that the associated unit is up and running. Table presents the flow rates of the electric energy and fuel streams that can be optimized. Table shows the base case and optimal results for the amounts of utilities that compose the objective function, as well as their prices and corresponding operating costs. The examples show that lower cost alternatives are obtained with the optimization approaches. These alternatives would not have been considered in real-world operation, based on the configurations that are usually operated in the plant. Moreover, these are practicable solutions that satisfy the plant constraints and the set of utility demands. In the OptiFOR case study, the demand profile results from frequent operational abnormalities, such as the shutdown of Unit US3, loss in the electricity supply from the third-party concessionary that is responsible for 25% of the electricity demand, shutdown of the turbo expander/electric generator unit that satisfies part of the electricity demand, and the shutdown of the L572 heat recovery boiler, which reduces the availability of the steam generated by the recovery of the energy from the process. Due to unit's shutdown, it becomes necessary to relate all flow rates to, and from, the process units and headers, with binary variables, that represent their operational state. The model must account for the loss of revenues from shutting down the process units. This is done by incorporating the revenues from the process units and multiplying them with binary variables that denote their operation in each period. The optimal solution for OptiFOR is presented in tables, where the flow rates and operating state of the main units are shown for the 4 periods. The figure depicts the main currents for all periods. The table presents the results of the utilities that are considered in the objective function, as well as their unit prices and corresponding operational costs. It is important to note that in case 4, as there are many utilities involved in the multiple time periods, it is not straightforward to analyze the effect of abnormal conditions on the operation. The optimal operating costs obtained in time periods 1, 2, 3 and 4 are $3,472, $3,472, $4,334, and $4,695 per hour, respectively. The revenue loss due to the shutdown of Unit US3 was $41,846 per hour. Finally, the last case study presented consists of a problem with 12 periods. For the first time periods, the data are the same as the OptiFOR case and from then on with variable utility demands. The optimal profiles of the main utilities, electricity, superheated steam, water, and fuel and natural gas are given. The next step is to energetically integrate the system, with the entire refinery, to further improve the operation of the system. More complex multi-period scenarios were studied that consider the existing flexibility in the industrial plant. These correspond to changes in the operating conditions and in the configuration of the processes, interruption of electric energy supply from the local concessionary, equipment shutdown, for example, propylene unit, turbo expander electric generator, and results in a variable utility demand along the time periods and generated an average savings of 3 to 5%. The MILP is currently integrated with the refinery database for the planning of the refinery utility system and effectively optimizes the financial performance of the thermoelectric plant with no capital investment. The Petrobras mathematical model can accurately represent the topology and optimize the operation of the real-world system under different utility demands and abnormal situations in single and multi-period scenarios. The model is currently integrated with the Petrobras plant database and used for the planning of the recap refinery utility system, achieving up to 10.7% reduction cost in static optimization for redesign the configuration of the service plant, and 3 to 5% average savings for dynamic operation of the integrated systems. All this in controlled experiments. Like Herbert Simon, Hypothalamus Artificial Intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.